Okay, so this is going to be the speed control aspect of the motors that we're looking at. We did see obviously some speed variations when I first turned the rheostat for the auto transformer up, and that was varying the input voltage. And so that has an effect on both the field winding here, right? Because again, when we get up to full voltage, this sees 120 volts, this sees 120 volts, I guess, right at startup, and then the counter EMF would limit how much voltage is in there, also limiting current, limiting torque. But this is always going to see that 120 volts, so it's going to stay fairly constant. But if I was to turn the rheostat down and limit the voltage here, it's going to have a limiting voltage. It's going to reduce the voltage here and there, and so then that obviously is one way to slow your motor down from base speed. And even when I turn this this up here all the way to 125 volts on this rheostat here, it still doesn't get up to base speed, because base speed on this motor is rated at 1750. So that means that because I've got that rheostat there turned down to 0, essentially I've got, I guess I've moved it all the way past this resistance here, that I'm not offering any resistance in here. So I've got the maximum amount of lines of flux in there, and if I've got the maximum amount of flux lines in there, then I'm producing probably the most counter EMF I'm going to produce at that point, and that's why it didn't get up to the 1750, it only got up to 1400 and something, because it just couldn't do it. But then what I'm going to do is we'll get it to base speed by adjusting this here and reducing the amount of flux lines in here, which will reduce the amount of counter EMF here, which will allow the motor to get more torque and speed up and get to there, and then we'll bounce it off and we'll get it to 1750. And then we'll start doing the experiments where we start above base speed, below base speed. Okay, so let's get it up to 1750, and then we'll start doing these experiments. And there's 3 methods that we're going to use. The first one, obviously, I'll just move this around a bit, and you'll just see here, and you can see it on the tack there that the speed is going to change. Really basic. And then the next one, we'll do I'll take this switch off. Right now I have it bypassed, but it's bypassing this resistor bank here. And then I will take the bypass off, and then we're going to add some resistance into here. So that's what that resistor bank is this. And I'm just going to start flicking resistances off. Right now they're all in parallel, so I have the least amount of resistance in there as possible. And then, so it's kind of like here, and then I'm going to start turning these switches off, which means that it's going to start increasing the amount of resistance that armature seeks, and that should be below base speed. Okay. And then we're going to fiddle with the one on the front of the console here, and that will be for the field winding, and that will get us above base speed. Okay. So this is for above. And this one is for below. This motor here is rated for base, I guess, put that in here, is 1750 RPM. Power this up. Okay, 125 volts on the armature, 125 volts on this here, and we're still only at 1465 for RPM. So I'll just adjust this, so that's what I'm getting there. I'm not even at base speed yet, so I do need to do some adjustment in the field. put a little bit of load on it just to smooth it out.
Oh, ah, there you go, jinxed it.
Yeah. Okay, so just by varying this input voltage, I'm going to reduce the voltage in both the field winding and the armature. You'll see that it goes down, right? Okay, we'll just go back up where we were before. Pretty close. So that's base speed. So that was the first method that we can do, but it's again affecting both portions of that shunt motor, armature and field. The next one we're going to do is the below base speed, and now I'm going to switch it so that I'm not bypassing these resistors anymore, and I'm going to put them in. There's going to be some resistances right away, so you're probably going to see it go down a little bit, but not a lot.
How much resistance do we have there?
I don't know, I have to calculate it all out.
Okay, so they're all parallel?
They're all in parallel. So it slowed it down quite a bit. Okay, so if I start taking these off, it's going to get even worse, or slower. And then you can see that the voltage is really going down in here.
Wait, what? I thought you had them all on.
What?
I thought you had the resistance on there now.
I've got them all on.
Yeah, now you take them off and it slows down.
Yeah, maybe I had too much current or too much load on it. I guess it was slowing it down too much. Didn't have enough torque. Come on. Get it back up to base speed. Yesterday when I did this, I didn't put any load on it, so that might have been why it slowed down so much. Close enough there. Okay, so now I'm going to just do this. There's kind of here, sort of balance itself out at about that. And then, just slow it down. We're about 97 volts for that armature. Then I'm just slowly reducing the voltage from here by putting more resistance in there. And now I'm down to about 93. Starting to slow down. 88, 87. And the resistance values get smaller and smaller. They're really high up here, high resistance values. But in parallel, it doesn't seem like it's that much current. It really drops significantly as I get further and further over here. 66, 64. It's really going down. And finally the last one here. It's really dropping. Putting it back in. And the motor speeds back up. So that's, one way of doing that, controlling it. When you've got some heat coming off of here, because, again, we'll talk about that in a second. So that's the one way of doing that. So that's two methods of doing below base speed. And now the field winding here for above base, start cranking this up, it's just going to get faster and faster. Not liking that. All getting warm. Six. Oh, reverse. Sometimes it's hard to get it back. We'll reduce the voltage here. The wire is quite hot. All right. So this method we're doing here, again, we've got a rheostat in here. We've got some power dumping load resistors there. The only one that wasn't a resistor, I guess, is this auto transformer here. But this is one of the methods that they originally came up with for speed control of a DC motor. Probably not the best, kind of inefficient, because again, if you feel that, and again, this is discolored up here because again, this ohmite potentiometer up here, rheostat, gets fairly warm, and even the lamicoid underneath it's all kind of discolored because of the heat coming off of that. So when we're doing above base speed, again, you're putting a certain amount of resistance in here. The more I do that, the less voltage would be here, and I have a higher drop in voltage up here. Obviously, some current. You need some fairly significant resistors in there to do that, or a fairly heavy-duty potentiometer. And it's giving off heat. And that's inefficient. You don't want to be. You're trying to do, change the speed of the motor, not create a heater. So that's not efficient use of your current that you're feeding to a motor. Same thing here. If you're trying to do below base speed and you're trying to run a motor that's rated at 1750, but you're constantly wanting it to run at 900 RPM, well, you're going to have some significant heat coming off those resistors here to drop enough resistance, or have enough resistance and have a high enough voltage drop here to slow this motor down that much. So that's inefficient too. So when we get into electronics, you're going to see that they've come up with much better ways of doing that. There's DC drives and stuff like that. Don't use that. They don't use resistors for that, power loads and stuff like that to drop resistance, or to have a voltage drop through the resistance. In fact, we would use electronics. And so we'll have what we refer to as SCRs in place of this. And an SCR is essentially a solid state switch. And when we start talking about, when you learn about DC voltage a little bit more, oftentimes they refer to DC voltage as an average voltage. So what this does here is it'll switch the load on, this field winding being the load. It'll switch it on, switch it off, switch it on, switch it off, switch it on, switch it off. And you get these pulses of, it's 125 volts full on pulse, and then it's off for a certain portion of time, then it's on for a certain portion of time, and then off for a certain portion of time. To the coil, it really doesn't matter, But what it will do is it'll have an average voltage of so much, right? So it's almost like if you were to go to school, well, and you're in trade school now, but if you were to, back in high school, I wouldn't do any of my assignments, and then I would come in and write a test, and somehow pass that. So my average was really low because I didn't hand in all these things. So it's kind of like you get, maybe you didn't hand in this assignment at all, and then you hand in the next one, and then you handed in nothing, and then that would affect your average, right? Because you're getting a 0 here, and then maybe you're getting 90, right? Or in this case, it's 100%, right? You're getting 100%, and then 0. And then, so if you had the same off times, the length as the on times, you'd end up with a 50% average. So that would reduce this from 125 here, right, down to what is half of 125? 62 and a half, right? 62.5, right? If you had it on for half the time, off for half the time, you'd end up with an average voltage of 62 and a half. And that's how they do that. Same thing for below base speed. You would do the exact same thing. You'd use solid state electronics. So that's what our drives are. And we have those, when we get into the electronics lab, we'll show you that. And
basically blocks the negative part of the sine wave?
That's rectification, right? So
I was kind of curious, like, it doesn't like a flicker or anything. Like, with that solid state, this is turning on and off. Like, how do they correct the flicker you get?
That's the rectifier in there.
you don't really get a flicker because what it's doing is it's just coming in partway through the DC pulse. And so first half of the DC pulse is off, and then the second half is on, or something like that, depending on where you phase shift that in, right? But that's how it works. Flicker. You'll see, when we do the pulse width modulation, that's what it's called. When we do it through an incandescent light bulb, we get no flicker because it's purely resistive load, right? But when we do a motor like that, you will see on the oscilloscope, you're going to see some weird things happening because of backfeeding and stuff through the inductive portion of the motor. So it does look a bit weird, but it works really effectively. One of the other things with the shunt motor here is that if you have a bad connection here, so it's loose or something like that, you can end up with kind of almost simulating this, right? High resistance, which means you got really low current in here. If you got really low current in here, but still enough to give you directions on your magnet, right? Still creating a north and a south. You're going to end up with very, 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 very little counter EMF in the armature. But you're still going to have enough for the rotor to have some spin in direction, right? It's probably already spinning, but now you're just giving it a little bit. And because of the real lack of counter EMF, because of not really cutting many lines of flux, you're going to get a huge amount of torque. And that's really what I did here. That's why you heard that go like that. But it can get even worse when you have a loose connection. At least at that point, I would get, some resistance. But if you get this loose connection here, I would get high resistance, but you can get even higher resistance with a loose connection. And but still, it'll make contact again. What I'll do with the shunt motor that we have, it's just these ones are too big. But what I usually do is I put just a single pole switch in, and I'll put it in here, and I'll just keep flicking it. So it kind of gives you some magnetic domains, and then no magnetic domains, and then some, and then, and it's just enough to keep the rotor going. But it's enough that the magnetic flux lines are so weak, right? Again, thinking of that average voltage in here, I create a very, very low average voltage, and I got that one up to 5,000 RPM. Yeah. Sounds like a jet engine going off. But it's kind of one of those things that you can do. I just can't do it with this one because it burns that switch and I don't have anything bigger to do that with. But that's just, again, some of the speed control that you get with DC motors.